Just to do an example as to how this works, let's go back to the two-state system, which was the two-state system. And so it had two energy levels, 0 and epsilon, like this. And we wrote down the partition function for this case. And it was 1 plus e to the minus epsilon over kBt. So now let's calculate the average energy of this. I'm going to use now my derivative formulas. So it was kBt squared over z d by dt of z. So kBt squared, here I've got 1 plus e to the minus epsilon over kBt. And now I got to take the derivative of the top, right? Of the z, right? d by dt, 1 plus e to the minus epsilon over kBt. Okay, the derivative of 1 is 0, so that's easy. And kBt squared, 1 plus e to the minus epsilon over kBt. And then I've got the derivative of the inside here, e to the minus epsilon over kBt, times the derivative of the exponent from the chain rule, which is minus epsilon over kBt. Okay, and this thing here is equal to epsilon over kBt squared, taking the derivative with respect to t. Derivative of 1 over t is minus 1 over t squared. And then you see that there's a kBt squared here in the denominator, which cancels this guy. So what do I get? I have an epsilon, e to the minus epsilon over kBt, 1 plus e to the minus epsilon over kBt. Okay? And you can make this a little bit simpler by writing it, by multiplying by e to the epsilon over kBt on the top and the bottom. Sorry, plus. And then I get u is equal to epsilon on the top divided by 1 plus e to the epsilon over kBt. So there's a formula that I got for the energy of this system just by knowing the partition function and doing some calculus. Let's go a little further. Let's calculate the entropy of this system. Okay, so let's focus a little more on this two-state system. So we already have a formula for the energy, but let's try to determine the entropy of this two-state system just using the partition function. So we have the partition function z here, and what I need to do next is calculate the free energy. That's minus kBt natural log of z, which is minus kBt natural log of 1 plus e to the minus epsilon over kBt. Now to calculate the entropy S, I could do it two ways. I could take the derivative df dt at constant v with a minus sign, or I could use the laws of thermodynamics, well, the definition of F, to write it like this, which was u minus F over t. I think the second one is easier in this case because I already know u, so I'll just use that one. And so then I get, what is my entropy? Entropy of this system is u over t, which we calculated on the previous slide. So it's 1 over t times, this was u that we calculated earlier, e to the epsilon over kBt. And then I have to do minus f divided by t. So f has a minus sign into it, so if there's a minus f is going to come with a plus sign, plus kb, there's no t because the t cancels, natural log of 1 plus e to the minus epsilon over kBt. So that's the expression for the entropy of this two-state system as a function of t. You can check the units. So always good to check the units. the units of KB have the units of entropy. That's joules per Kelvin, so that's good. So this term has the right units. And this term has the units of epsilon, which is joules divided by Kelvin. So that's also joules per Kelvin. So the units are good. Each term has units of joules per Kelvin. And so this is the formula that we have. Now, something interesting to look at is what happens when t goes to infinity. That's the example we've been focusing on a lot. If t goes to infinity, this first term goes to 0. So I'm going to have s is going to be equal to 0 because I've got a 1 over t showing up there. So if t goes to infinity, that whole term goes to 0, plus kb natural log of 1 plus e to the minus epsilon over infinity, which is e to the 0. So it's kb natural log of 2. And does this look kind of familiar? Remember, in an isolated system, S was kb natural log of omega, or that was the number of microstates. And if the temperature is really, really high, the particle can easily move between these two microstates without any trouble. So it has those two microstates are both equally probable. And so then I have the same kind of situation as I had with an isolated system. So this agrees with the intuition we had before. So that's an example of how you calculate entropy, internal energy, free energy, all by knowing the partition function. So all I need to do is calculate this partition function and then do some calculus and algebra on it in order to get all of the thermodynamic quantities you want. So let me try to summarize this central topic of statistical mechanics, which is the partition function. We learned how to calculate this partition function. Basically, you just have to add up all of these factors, these Boltzmann factors, for every state in the system. And what you're doing is making sure that all the probabilities add to 1. When the sum of the probabilities has to add to 1. And so that's how you calculate it. Once you know this z, this partition function, it's incredibly powerful. You can use it to calculate all kinds of things like pressure, energy, internal energy, entropy, just by doing some mathematical operations on it. So that's really, really important. So this partition function is the central object that sort of everything comes from this. The next steps are, we did an example of a toy system which had 2 states in it here, so that's obviously not. Well, there are some systems which behave this way, but hasn't been really the focus of this class. The next step to go forward into something more physical would be to try to calculate the partition function for an ideal gas. So that obviously is more complicated than a 2-state system, but nevertheless you can do it. And once you have the partition function for an ideal gas, you can use it to do to prove all kinds of interesting things. Like these are things that I claimed earlier, which I didn't really prove to you, that the energy of the ideal gas depends only on the temperature. That's something you can prove using the partition function. You can actually prove the ideal gas law, so that's kind of an amazing thing that normally people say this comes from experiment, but if you know the partition function for the ideal gas, you can prove this is true. And then finally you can get something which we haven't seen yet, which you can determine the formula for the entropy in the ideal gas. And that's a really, really interesting formula that you need the partition function to calculate. We know from before, we know that the change in entropy of an ideal gas, we had a formula for that, was Nm times CmV natural log Tf over Ti plus R natural log of Vf over Vi. So I can calculate the changes in the entropy from what we've done in thermodynamics, but if I want to know what the actual entropy is, not the change, that's something that we haven't been able to access using thermodynamics. You need statistical mechanics to do that. And that's something you could get from the partition function of the ideal gas. I should say that these next steps are things that I normally do in the course, kind of try to finish the course using this, but in 2020, we won't have any time to do this. So this will, we've run out of time, which is sad because it's really, really interesting. So I'll post those lecture notes, which you can look at if you're interested. But otherwise, this lecture on the partition function will be our last lecture in 2020. And if you're interested in these really, really interesting things, I recommend doing some reading on your own, or taking a higher level course in statistical mechanics wherever you can find it. There's really so much interesting stuff that we just didn't have time for. I mean, there's never enough time, no matter how long the semester is. So, but this will do it for us for the new material, and I'll post some other things in case you're interested, but only up to this lecture on partition function. That'll be the stuff covered on the final exam.